Okay, hello doubles. How's it going? This is just a video basically taking you through part one of the homework, the test preparation questions. And I think the first half actually is easier than the second half because the second half has de Moivre's theorem. So obviously that's going to be one of the tougher bits. But maybe you don't like this first question. This, though, I would consider a much more kind of typical question, actually. Basically cube rooting a real number or a complex number. When it's just z equals that, we're going to cube it. But first, it wants us to just turn Cartesian form, excuse me for the yawn, turn Cartesian form into exponential form, if you like, or modulus argument form. Okay, so that's what we're going to do. So this isn't too bad. If you draw a quick sketch, it makes it much easier. We're going 3 across, 4 up. Okay, so I mean, r is quite obviously 5, isn't it? Like in the re to the I format because it's the distance from the origin. And theta, well, tan theta is going to be 4 over 3. And that does actually give theta equal to like 0.927, 3 sig fig. It doesn't say how accurate it wants it, so I'm going to leave it like that. So z equals 5e to the 0.927i. What a weird way of expressing a number, eh? But it is useful. Okay, and that 0.927 is in the range, not a problem. Okay, B, part 1. Find the Cartesian coordinates of the vertices of a triangle formed by the cube roots of z when plotted in an Argand diagram. Give your answers correct to 2 decimal places. Okay, so this is basically cube rooting. We know z equals 5e to the 0.927i. Now, what I like to do actually in these questions, and it might look a little bit different to the way the textbook approaches it, but I do think the textbook makes a bit of a, I don't know, it really makes it seem like a really long task, this, and it's not. You just need to use the principle that if you add 2 pi to an angle when it's in radians, you get exactly the same sine and cosine values when you do sine and cosine. So if you can imagine this as 5 cos 0.927 plus I sine 0.927, the point is if you add 2 pi to 0.927, it's exactly the same value. So I'm just going to write down other possibilities for z right now, because all this is going to do is just rotate this 2 pi radians or 360 degrees. So it's definitely going to be the same complex number. So I'm going to write it down as 5e to the 0.927 plus 2 pi I, and then 5e to the 0.927. I'm going to do minus 2 pi I. Yeah, and all I'm really doing there is saying both of these, if you were to turn it eventually into Cartesian format, or even if you express it in like the r cos theta plus I sine theta form, you're going to see you get exactly the same values after you do sine and cos of these numbers. It's because sine and cos repeat every 2 pi. Okay, so what I'm going to do now is I'm going to cube root. So z to the third equals, and this just gives you the 3 roots right away, which I like. 5 to the third. Okay, so this is going to be e to the power of, we need to find a third of that. Now, I noticed at the end that my answers were slightly off from the mark scheme because I'd introduced rounding errors. Be careful about reintroducing rounding errors. You might want to work to 4 decimal places here so your answers don't get thrown out for 2 decimal places. Okay, I'm going to write down 5 to the third, and now I'm going to have e to the power of all of that over 3. 0.927 plus 2 pi, but then we're going to divide by 3. I. And the same for this one, 5 to the third, e to the 0.927 minus 2 pi, all divided by 3, I. Yeah, and as you can see, I'm just using index laws there, really. I'm putting the power to the, I'm multiplying the power by a third because it's being put to the power of a third. And now I can just change these into Cartesian form by thinking of it like this. I've just got to do 5 to the power of a third cos of 0.927 over 3 plus I sine of 0.927 over 3. And that's the easiest one to get. And I'm just going to work out what that actually is. When you do it on a calculator, you should get 1.63 plus 0.52i. Now, I mean, if you're using here the exact 0.927, not the rounded one. I'm obviously 0.927 has been rounded, but use inverse tan of 4/3 and divide that by 3 and press cos and press sine, and Nate should give you those to 2 decimal places after you've timed it by 5 to the power of a third. Okay, for the next one, if I can just shove the screen over a bit here. Now I'm looking at this one, and it's going to work in exactly the same way. Call that one Z1 if you like. Z2 is going to be equal to 5 to the third times by cos of all of that stuff, so 0.927 plus 2 pi over 3 plus I sine of 0.927 plus 2 pi all over 3. Multiply it all out. Don't forget to times by 5 to the third at the end, and you should get minus 1.26. Why am I putting a comma there? Plus 1.15 I. And your Z3, very, very similar. We're just going to plug in that now. We're going to get 5 to the third cos of 0.927 minus 2 pi this time, divided by 3 plus I sine of the same thing. So it's definitely a bit of a tedious sort of cranking out of the numbers here. I don't necessarily approve of these questions because it feels so calculator dependent. And I think it comes to that, rounded correctly to 2 decimal places. And those are your 3 roots. Remember as well, yeah, on a calculator, you can check this, because what I suggest you do is you take that last one and plug it in. I might try it now on my one, because our calculators actually work with complex numbers now, don't they? If you go to complex mode, it's like number 2. So I'm just going to type in this last one, minus 0.36 minus 1.67. Now, if I can remember how to make I appear. Yep, it's appeared. And I'm going to put this to the power of 3 and see what my calculator says. Okay, I end up with a number very close to 3 there, 2.965, and here a number very, very closer to 4.008. So it looks like I've done it right. My point is there on a Casio FX911EE class Wiz, it will check that for you. So those are our roots. It's a bit tedious trying to get them. Write down the name of the triangle. It's an equilateral triangle. Equilateral. I can't spell. Equilateral triangle. Yeah. And that's going to be the case whenever you find the nth roots of a number, real or complex. Yeah. As long as it's just a number on its own and not a polynomial. Like essentially we've got like this one, then we've got like 1.63, 0.52. Oh, yeah. And then we've got like maybe one over here, one down here where it's both negative. It should be though, let me just get that angle right there, more like that, but it should form an equilateral triangle. And that's because basically whenever you find these nth roots of unity, that always makes the same thing. And it's because if we times each one of these, well, this is like Z1, Z2 and Z3. Yeah. The point is, when we times them by themselves 3 times, we eventually get to 3 plus 4i. You always get this with nth roots of unity, but it's to do with the fact that whenever you multiply by a complex number, it's just a rotation. They're just rotating 2 pi over 3 radians. If you saw that 2 pi over 3 earlier in there, if I can just highlight that, that's the reason why they're rotating. Yeah, just 2 pi over 3 each time, isn't it? You can see it. The modulus is staying the same, but the argument's just rotating 2 pi over 3 in that direction and 2 pi over 3 backwards underneath. That's why they're evenly spaced. Okay, so that was the first question. Not too bad, really. Next question. I don't think this one's too bad either. I really don't. So we've got a polar equation. We've got to find let's just try sketching this polar equation first. Okay, when theta is 0, when you're on the initial line, you'll notice that cos of 0 is 1, so you get 2 plus 1, 3. 3 times 3 is 9. What about when theta gets to pi over 2 when we're over here? Well, cos of pi over 2 is 0, and you get 2 times 3, which is 6. What about when theta is pi? Okay, cos of pi is minus 1. 2 minus 1 is 1, and 1 times 3 is 3. So we're going to get something like that. And they want us to work out the area enclosed by this curve and the initial line, so just this area up above here. Now, the way to do integration is half r squared d theta between the limits of 0 and pi here. Yeah. Now, r squared is simply going to give you a half times by 9, but I'm going to put the 9 outside, pi and 0 here, and I'm going to square the 2 plus cos theta. So that's going to give me 4 plus 4 cos theta plus cos squared theta. Naturally, the difficult bit of this to integrate is the cos squared theta, and cos squared theta is exactly the same as, let me think about this, cos 2 theta plus 1 over 2. And that's a standard double angle formula we use for these kinds of questions. And so we're going to integrate between pi and 0, 4 plus a half, well, let's call that 9 over 2 straight away, plus 4 cos theta, plus a half cos 2 theta, d theta. Okay, let's integrate it then. We're going to get 9 theta over 2, plus 4 sine theta. Now this is going to integrate to a quarter sine 2 theta between pi and 0. No, pi over 0 doesn't make much sense. Okay, between pi and 0. Go away. Okay, so carrying on, we're going to get 9 pi over 2 plus 4 sine pi, well that's 0, plus a quarter sine 2 pi, well that's 0. Now always never assume that the next answer, because there's 0 there, is going to give you 0. I think it does, because 9 times 0 is 0, 4 sine of 0 is 0, and a quarter sine of 0 is 0. And so we will look good there, but never assume that that's true. And so at the end, we're going to get 81 pi over 4, and it's done. So that one's not too bad. What about number 4? Number 4, okay, given that y equals inverse cot of x, find that, or show that dy by dx is minus 1 over x squared plus 1. So we can't use chain rule or anything like that here. We've got to do this a long way and say initially, okay, so cot y equals x. So dx by dy is, now cot differentiates to minus cosec squared y, and therefore dy by dx is going to be minus 1 over cosec squared y. Now, the secret with these questions is always a trig identity. 1 plus, let me give myself some more space here. I'm going to say it over here in a little bubble. 1 plus cot squared y is cosec squared y. And so 1 plus x squared in this case is cosec squared y. And so I've got minus 1 over 1 plus x squared for my dy by dx. And that's part A. Hope that wasn't too tricky. Very similar. That's really can be asked in single maths. It really can. I don't think that's too unusual. Okay, question 4b. Okay, right. Let's write this in terms of partial fractions. 6x squared minus 10x minus 9 over 2x plus 3, x squared plus 1. Well, we need the general format, and it's one of these new irreducible quadratic factor ones. So we're going to have a bx plus c, which we need to write over x squared plus 1. At which point it's probably best to say, okay, so 6x squared minus 10x minus 9. That's going to be equal to a times by x squared plus 1 plus bx plus c times by, never got enough space on this page. Okay, 2x plus 3. It's nice to have this original one written down. Oh dear, my handwriting's getting worse. Okay, so what are we doing now? We're doing the old let x equal trick, and the most obvious one to pick first is minus 3 over 2. Because if we times by minus 3 over 2 there, we get minus 3, add 3 is 0. So what are we going to get here? Well, I keyed this into my calculator earlier, and I could see that the left-hand side is going to give me 39 over 2, and the right-hand side give me 13 over 4. So I get 13a over 4. Now, if I times that by 4 over there, I get 2 times 39, which is 78. And 78 divided by 13, I think is 6. So a equals 6. Once you've got that, you could be you could enjoy yourself and let x equal I suppose, in order to knock out this first bracket. But it's easier to probably just note that you've got a 6x squared here on the left hand side, then you've got an ax squared on the right hand side, and a 2bx squared on the right hand side. And as x is 6, it follows that b equals 0. So that's just equating coefficients. And then you can see that as a is 6, b is going to need to be 0. Okay, for the last one, should we equate coefficients again but use the final term? Because we can see that minus 9 on the left-hand side should equal a plus 3c. Now, if a is 6, you're going to get minus 15 divided by 3, so c is minus 5. And you've done it, yeah? We've expressed it in partial fractions. Well, if they want us to express it in partial fractions, we can now. We can say that's the same as 6 over 2x plus 3 minus 5 over x squared plus 1. Okay, so that's cool. Now, in the next question, notice the top is not the same as the one there. Oh, they're just trying to confuse you. They're good at confusing people. They just put a little landmine in here and a landmine in there, and it's not too bad, really, as long as you keep your wits about you and watch out for something like this. So, yeah, how is that one different to this one? Well, it's exactly the same because we want to use the previous answer. Except we need to now add on. So this is just writing down that. How can I change that into this one? Well, if I added 2x and 3, then I'd be there. Okay, that's great, because naturally this next one simplifies if I cross those out, and this one can be written using the partial fraction. So what have we got to integrate? We've got to integrate 6 over 2x plus 3 dx minus 5 over x squared plus 1, but plus 1 over x squared plus 1, so that's just minus 4 over x squared plus 1, and it's worked out nice. This first one integrates to 3 ln 2x plus 3. And this last one, well, you've got a choice here. You could write that down. I must admit, when I looked at it, I thought, oh, that's the arctan one. And so I just wrote it down straight away as minus 4 arctan of x plus c. Yeah, but you don't have to do that, because you've shown in the first part that if you've ever got minus 1 over x squared plus 1, well, that integrates to plus cot x. So it is absolutely the same as saying plus 4 inverse cot of x plus c if you want to. It's completely up to you. Okay, let's do the last one of this part. Write down the Maclaurin's expansion for ln of 1 minus x as far as the term in x cubed. Now look at this, it's worth 2 marks. That means they definitely don't want you to do that full kind of like find the first derivative, find the second derivative, find the third derivative. No need, we can use the standard results. Yeah, that's what I mean. You don't have to use that. You can use this standard result. So let's do it. Looking at that, they want ln 1 minus x. So I'm just going to replace all x's in there with minus x's. And I'm going to get ln 1 minus x. Right, replace that x with a minus x. Replace this one with a minus x, but I'm squaring it, so it becomes plus x squared over 2. So that's minus x squared over 2 still. That sign's not going to change. But the next one, after you cube minus x, you definitely get minus x cubed. And so that's going to be over 3. Done. So use those standard results when you can. And part B, show that. Will do. Right, okay, so looking at this, I don't mind the minus 2 sitting there, because I can just times everything by minus 2 at the end. I'm going to break this up though into ln 1 minus x, because I know what that is, minus ln of 1 plus x all squared. And then I'm going to think, okay, I can definitely write that, because I've got it above. This I can't yet, but what about if I was to move the 2 down here? Then it will be all good. So that's what I'm going to do. So I'm going to have minus x squared over 2 minus x cubed over 3 minus 2 times open bracket, and then I've got exactly the same of what I've got here, x minus x squared over 2 plus x cubed over 3. And I can simplify that, so I'm going to get 2x minus plus x squared plus 2/3. Oh, maybe I should simplify the ones in the brackets first. It'd probably be easier. I can just double everything at the end. So I've got minus 2 times minus x minus 2x is minus 3x minus x squared minus or plus x, minus x squared over 2 plus x squared is going to give us plus x squared over 2. And then minus x cubed over 3 minus 2/3 x cubed is going to be a minus a whole x cubed. Now all I've got to do is times them by 2, so I get 6x minus x squared plus 2x cubed. Let me just look down at my notes and check I've got that right. Yep, that looks good. And that's it. Okay, hope you enjoyed the first part. I'll be popping the second part up soon, but well done and thanks for listening.